Reading week 10. This week's main physics idea was the Faraday's law and induced current. To look at Faraday's law, we looked at a falling magnet and calculated that the time-changing B field produces curly E fields, as you can see on the right. And we can apply the right-hand rule to figure out the direction of the curly E field. And from this, we learned that we can induce current on the wire loop, and as long as it is conducting wire, it should induce current. Otherwise, if it's insulating material, then it shouldn't conduct current. And we figured out the energy source for the EMF that creates this induced current comes from gravitational potential energy. As the magnet falls from the top to bottom, the gravitational potential energy decreases, and therefore this energy then goes into the EMF that produces induced current. We also looked at Lenz's law, which shows that magnetic field from induced current opposes change in flux. And what I already knew based on this week's material is the right-hand rule, and I knew the concept of conductor inducing current, and I was also aware of Newton's third law that we use to calculate the force on the magnet by loop, as you can see on the bottom right, where it is in the same magnitude as the force in loop, but in opposite direction. And what I did not already know was the Faraday's law. It was a new concept for me, and it was interesting to see how the flux, the magnetic flux that we learned last week, actually applies to this new rule. Something interesting that I learned is the application of right-hand rule and how handy it can be. You can use it to find direction of curly field or current or the magnetic force. In this, not only in this model, but also in other models that we learned before. And it was interesting to see the principles learned in Physics 1 was coming back. For example, the conservation of energy was used to show that the energy source for the EMF, which created the induced current, is actually gravitational potential energy being transferred into the EMF. And Newton's third law was appearing when we had to calculate the force on the magnetic dipole, because Newton's third law states that two forces are equal in magnitude but in opposite direction. And how this week's material relates to my major as electrical engineering is the idea of induced current comes upon when we are building circuits, and it shows that if a coil of wire is placed in a changing magnetic field, then a current will be induced in the wire, and this current will flow because something is producing an electric field that forces the charge around that wire. And something confusing was the difference between Faraday's law and the Lenz's law that we also learned this week. And based on this Khan Academy source, I learned that Lenz's law is the consequence of conservation of energy being applied to electromagnetic induction. And while Faraday's law tells us the magnitude of the EMF that's produced using the derivative of the change of the magnetic flux of the falling magnet, and on the other hand, the Lenz's law tells us the direction that the current will flow. Basically, it's stating that the direction is always in a way such that it will oppose the change in flux which produced it. And we just basically used a negative sign in front of d flux over dt to show this relationship. And this means that any magnetic field produced by an induced current will be in the opposite direction to the change in the original field.